Hey, how's it going, guys? So today we're going to be going over feathering for extravascular doses. And there's two types of feathering for this final exam. There's feathering for IV bolus, 2-compartment, and then there's feathering for extravascular, 1-compartment. So we're going to do the extravascular today. And it's usually oral. It could be anything. It could really be anything. It could be like rectal or something like that. But it's usually oral, but not always. And like I said, it's 1-compartment. And this is the equation to, simplify this. It's C is equal to B times E to the negative KET minus A times E to the negative KAT. And usually, I want you guys just to keep this in mind. A and B are going to be equal, except if there's lag time. So, okay, let's get into it. So what is feathering? Feathering is really just taking the graph of this equation. So this C equation gives us this graph, right? But we're not going to know. We're just going to be given points. We're not going to know what B is. We're not going to know what KE is. We're not going to know what A is, and we're not going to know what KA is. So the purpose of feathering is just to find these points, find these values, sorry, based on the points we're going to get. And I'll show you right now what I mean. So this is from the textbook. Oops, sorry. From the textbook. I can't actually erase that. That's awkward. Okay, so for example, this might be something Xiao's going to give us. He's going to give us just different points on a graph for a certain graph and ask us how to find compute the equation which describes the plasma profile for this drug. So it's basically just asking us to find the variables in this equation and writing the equation out. So this is the equation for reference, and I'll just draw the graph of it. So the graph of it is like this. Kind of goes up, you see, and it goes down. So it starts at like 5.3. It's like right here, and then it'll gradually climb up. I think it peaks at 11. This is around 11. It's around 11, and then it goes back down to 0.810. Okay. So, how do we get started? So the first thing to remember is that, when Ka is usually bigger than Ke, and from the last video, this part gets canceled out first, right? So this part gets canceled out. So now we're left with C is equal to B times E to the negative KET. And this part only gets canceled out when time is big. So that means we're using, from the plots that he gave, from the points that he gave us, we're using the points where time is big. So 12, let's say 12 and 14, usually that's what you use. So I'm gonna just make two notes. So you got your point at 14 and you got your point at 12. And that's when time is big, right? 12 hours, 14 hours. If time is big enough, this part cancels out, so you're left with this. And what does this mean? C is equal to B times E to the negative KET. It just means that we just made another line. We just made this line. This the equation of this line is C is equal to B E to the negative KET. And we just made that. The cool thing now is that we can find B and we can find KE now, because this point is the y-intercept and that's B, and KE is just the slope of this line. So slope is equal to KE. And how do you find slope using 2 points? Well, you do ln of the concentration. So let's say 1.393 minus ln of another concentration, 1.801, divided by the last 2 points. So we got 12 minus 14, and this gives us KE. And the sign doesn't matter if it's negative or positive. We just want the value. So KE ends up being roughly 0.27 per hour. And what I like to do is just write my values down on the side so I don't get lost. So KE is equal to 0.27 per hour for the test, especially because you're going to work with a lot of numbers. Once you find KE, the next step is to find B. And finding B is easy because we can just plug in any time. So let's plug in, we could plug in 12 times 12, and then C would be 1.3 0.93 because, you know, any time it would be this concentration, right? And we'll find the y-intercept b, or we could plug in 14 as t, and we'll find, and the c is 0.810, and we'll find b. So let's just do, let's do 12. So if time is 12, concentration is 1.393, is equal to b times e to the negative ke we found is 0.27, and time is going to be 12. So if you do the math, b ends up being 36 micrograms per liter. And just, you know, as a note, I write it down on the side, 36 micrograms per liter. So now you have this whole equation, right at the top right, you have this whole equation. So now we're working with this equation. So we just solved half of it, you know. The hard part is pretty much done. Well, not really. Not really, just kidding. But we're working with this now. C is equal to 36 e negative 0.27 time, and we can, you know, bring this back in because we're not working with the terminal phase data anymore, the last 2 points anymore. Now we're looking at the whole thing, this whole, you know, curve graph. So now we need to find this portion, right, the right portion. And how do we do that? Well, we just isolate it. We just move the variables around. So this actually ends up being is equal to 36 e to the negative 0.27 times time minus concentration. So now this is what we're working with, and we want to find A and we want to find Ka. And how do we do that? Well, it's this is probably the most intensive part about feathering, is when you make the second feather. So we just made the first feather, which is the B line. Now we need to make the A line. And how do we make the A line exactly? Well, instead of using the last points this time, now we want to use the first points. And how do we do that? So what I like to do is I just like to make a T-chart. And I'll show you what I mean. So basically, as long as if we find the value of 36 e to the negative all that minus c, the value of c, we'll find points on this A line, right? So sorry, I'll make a use a different color. Okay, so if I make a point, time, column time, I like to do this. I really recommend this. It really organizes your numbers, and you will not 100% will not get it mixed up. You know what, let me just write this straight out. And then you have 36 minus c, aka this is also equal to this. So a lot of the values you already have. So time, we'll use 0.5. And 1 hour. Concentration, we're given 5.31 and 8.49. Now we need this value, right? And this value is pretty much the B line that we just got. So B line, what is the value of any point on the B line at? Time is 0.5 and time at 1 hour. So let's see what I get. Okay, so if I plug in time as 0.5, I'll get this to be around 31.5, and if I plug in time as 1, I'll get 27.5 roughly. Okay, so now what do we do? What does this mean graphically? So on the graph, we'll say this. So at time we said 0.5. The concentrate, the C on this curved line is 5.31. So 5.31. At time 1 hour, the concentration on this graph is 8.49. At time 0.5 hours, the concentration on the B line is, I'll use a different color, it's going to be 31, right? 31.5. And the concentration on the B line at 1 hour is going to be 27.5. So now it tells us to just subtract this. So we subtract this, which is 31, let's say 31.5, minus C at that time only, though. You can't subtract 31.5 from 8.49 because that's at different times. You have to do it at the same time. So that's why I like to do this table. It aligns everything up. So let's say we'll do 31.5 minus 5.31. And we get 26.2. Why are these colors so ugly? 26.2. And if we if you subtract the second row, we get 27.5 minus 8.49. We get 9. Let's say we just get 19. Okay. So what does this mean now? It means when you subtract 31.5 from 5.31, we get a point around right here, and that's 26.2. If we subtract 27.5 from and 8.49, we get a point around, I would say, like right here. And this lets us create another line, and this is the second feather. Here we go with my bad lines. The second feather. Oh my god. That's the second feather, and that's known as the A line that we have right here, which the equation is this. So, okay, so once we find this A line, now we can do the same thing. We just repeat it for the A line. So we got KE through this, and now we can just repeat it for KA. So now you want to take these points that we just got, 26.2 and 19, and plug them into the slope equation. So divided by 1 minus 0.5. And that gives us Ka. So Ka turns out to be, let's see, about 0.64. So I have like no space, 0.64 per hour. So Ka is 0.64 per hour. And now we can find A using the same thing. So we just plug in, we'll say C. Let's say C prime. C prime is equal to, we have Ka, so C prime, let's do, we could do 20, let's plug in 26.2. So 26.2 is equal to A, e to the negative Ka. Ka we just found is 0.64. Time is, at what time do we get a concentration of 26.2? Well, at 0.5 hours. And we'll get A, and A happens to be 36. So here is the cool part. We see that B and A are exactly equal. So now we know that it's extravascular. That's a way for us to check that it's, we did all our math right, that it really is extravascular dosing. So then if we were to find the actual equation, it asks us to compute the actual equation, we get C is equal to, what would be C is equal to B. This is the template. And we just plug the numbers in, and we'll get B is 36. 36 e to the negative, Ke is 0.27. 0.27. Get the time here, minus A is 36 also, e to the negative 0.64 times time, and this would just be your equation. So once you get this part, it's not going to be the end. Xiao's going to kind of want you, Dr. Xiao's kind of going to want you to find more, and you can find a lot of things simply based on this equation. So for instance, we know that in extravascular dosing, we know A, now that we know is equal, so A is equal to B, same thing, is equal to F times dose times Ka over V, right? So let's say the volume, this question wanted us to calculate the apparent volume distribution if the fraction of dose absorbed is 0.7. So we have this equation. So let's say, so now we have fraction of dose absorbed. So if I were to write on the side, so F is equal to 0.7. The dose we're given is a 100 milligram dose. Remember, it's in micrograms actually. So I'm just going to convert this straight up to micrograms. So 100 milligrams is, just have 3 zeros, 100,000 micrograms. Ka we found is right here. Ke is right here per hour, and then A or B doesn't matter. It's the same thing as 36 micrograms per liter. So now all we need is the volume. So we just isolate volume, and volume ends up being about let's see, 3.37 liters roughly. So the volume distribution is 3.37 liters. So this is one thing you can find. You can also find you could find, I guess, clearance. You can find clearance, and clearance we know is K times V. So we have volume now. And what K is it? We have K and KE will be KE, because that's elimination. Clearance is elimination. So we can find KE, we can find AUC. AUC we know. AUC is actually a special equation. You can use, I think you can use dose times F divided by clearance. We just found clearance, dose is, you know, that, F is that. Or there's another equation for AUC for extravascular only. For extravascular only, it doesn't apply to IV two compartment. It is B, big B over KE minus A over KA, and we know B and A are equal, so we can do that. I think we can also do I don't know, you get the point. You can find a lot of things. We can also do like rate of elimination. Rate of elimination is KE times X, or in this case it would be KE times dose times F, and that would be rate of elimination. So you gotta just play around with it. There are a lot of problems in chapter 12 that helped, and I would do them a couple times. Yep. So thanks. Next video, I want to do a lag time with extravascular, and that's going to be when A doesn't equal B. So stay tuned.